So how does the cost vary as we increase output? Well, to understand that, we're going to introduce the concept of an expansion path, which gives us a curve through all of the cost minimizing input bundles for different levels of output. We're of course going to fix the prices of the inputs when we do this. So let's go back to the example that we've seen previously, where we had the production function as the quantity of output is 1.52 times labor to the 0.6, K to capital to the 0.4, and we're going to fix the wage at $24 and the rental rate at $8. What we found was that the cost of producing 100 units was 2,000. So the cost of producing 200 units is actually going to be 4,000. Now, why is that? No, there's something special about this particular production function. It's a constant returns to scale production function. In the last chapter, we talked about that a little bit. It's because these numbers sum to 1. So if I were to multiply L and K by, let's say, 2, then the output is going to be multiplied by 2. Let's look at that a little bit more carefully here. 1.52 times 2L to the 0.6 times 2K to the 0.4. Well, that's equal to, I'm going to factor out the 2's. 1.52 times 2 to the 0.6 times 2 to the 0.4 times L to the 0.6, K to the 0.4. Well, this is just 2 to the 0.6 times 2 to the 0.4, which is 2 to the 1, which is just 2. So that's just 2 times 1.52, L to the 0.6, K to the 0.4. And this is, of course, the quantity of output that you would get if you just use L units of labor and K units of capital. So because we have constant returns to scale, so when you multiply the labor and capital by some number, it's equivalent to multiplying the output by that number. The cost is just going to be multiplied by the same factor. So to produce 100 units, the cheapest way to do it would cost you 2,000. So the cheapest way to produce 200 is just going to cost you, it's going to be twice that. Also, remember, when we solved this, we found that the optimal way, given the wage rate of 24 and the rental rate of 8, we found that the optimal capital was 100. This is to produce 100 units of output, and labor was 50. In other words, so to produce Q units of output at the wage rate 24 and rental rate of 8, optimal capital level is Q, optimal labor level is Q over 2. Just hang on to that because we're going to use it in a little bit. This just comes from the fact that when we solved it for quantity of 100, we found that K equals 100 was optimal. You can refer back to the earlier video for that. And then given that, we're going to use the fact that this is a constant returns to scale production function to conclude that whenever you want to produce Q units, well, you just need to use Q units of capital and Q over 2 units of labor. Okay, so the cost of producing 100 units is going to be 2,000. So the cost of producing 200 units is 4,000 and so forth. So we can draw an expansion path. So if we draw labor and capital on the horizontal and vertical axes respectively, we can draw a line through all the optimal bundles. We get 50 and 100 to produce 100 units of output. 150 and 75 to produce 150 units of output, 200 and 100 to produce 200 units of output, and so forth. So the cheapest way to produce 100 units is to use 100 units of capital, 50 units of labor, and that's going to cost you $2,000. The cheapest way to produce 150 units is to use 150 units of capital and 75 units of labor, and that's going to cost you $3,000. The cheapest way to produce 200 units is going to cost you $4,000, and so forth. And we just draw a line through all the optimal bundles of inputs, and we call that the expansion path. But what we want is eventually the cost curve. So, like I said earlier, you're going to use to produce Q units of output when the wage rate is 24 and the rental rate is 8. To produce Q units of output, you're going to use Q units of capital and Q over 2 units of labor. So the higher the quantity, the more capital and labor you're going to use. So what does it actually cost to produce Q units of output? So what is C of Q, which is really what we want to know? Well, C of Q is just the cost of the inputs that you're going to use. Well, you're going to use Q over 2 units of labor, which is going to cost you W times Q over 2. You're going to use Q units of capital, which is going to cost you R times Q. So it's 24 times Q over 2 plus 8Q. This is 12Q plus 8Q, which is 20Q. So that's your cost function. So C of Q is 20Q, and that's the cost function, and it tells you how much it costs to produce Q units given the input prices of 24 and 8. How did we find this cost function? Well, we solved the cost minimization problem, and that gave us the cost function. So once we know what this is, we can plot it. And so it would look something like this. In this particular case, it's going to be a straight line of slope 20. Cost of producing 0 units is 0. Cost of producing 100 units is 2,000. Cost of producing 150 units is 3,000, and so forth. Okay, a little word of caution here. We made our lives very easy by choosing a very specific production function. The production function, it's a constant returns to scale production function. In particular, it has the property of what we call homogeneity of degree 1. So when you multiply the inputs by some number x, it's as if you've multiplied the output by the number x. This is equivalent to constant returns to scale. Now, as long as your production function satisfies some homogeneity, so homogeneity of degree gamma, Greek letter gamma, such that if you multiply the inputs by x, it's as if you multiplied the output by x to the gamma, then doing the exercise that we just did is very easy. What that means is that your production function has the same returns to scale for all levels of output. But when the production function has different returns to scale at different levels of output, this exercise gets a lot trickier. So that's just something I want you to keep in mind, that the exercise we did is special because of this. And we can define marginal cost and average cost for the long run as well. So as we vary the quantity, we're going to have a marginal cost and an average cost. And these, of course, are going to, just like in the short run, depend on the cost function. So if the average cost is U-shaped, just like in the short run, the marginal cost is going to pass through the average cost at its minimum. Remember, in the short run, the average cost is U-shaped because we might have a fixed cost. So because of the fixed cost, you're going to have decreasing average cost at first, but then because of diminishing marginal returns, you might have a increasing average cost for higher quantities of output. In the long run, on the other hand, you're typically not going to have a fixed cost. So there's no diminishing, and you're not going to have any diminishing marginal return, since all of the inputs can be varied. So the average cost curves, the shape of the average cost curve really depends on the returns to scale. If the returns to scale are increasing at first and then decreasing, then you're going to get a U-shaped average cost curve. So if you have a U-shaped average cost curve, then at low levels of output, where the average cost is decreasing, you have economies of scale. At intermediate levels, you have where the average cost curve is flat, you have no economies of scale. And when the average cost curve starts going up, so when you have increasing average costs, then you have diseconomies of scale. In competitive industries, you typically have U-shaped average cost curves. In industries where the average cost curves are not necessarily U-shaped, so ones where you have very large fixed costs, for example, like in utilities or telecom, then those industries tend not to be very competitive.